So guys, now we are going to continue with the periodic properties of boron family. The next periodic property which we are going to discuss, that is electronegativity. They are more electronegative than group 2 elements. Okay, so electronegativity of these elements, as we know that as we move across the period, electronegativity goes on increasing. So more electronegative than group 2 elements. Okay, and as we move down the group, electronegativity decreases, because electronegativity is again inversely proportional to atomic size. Therefore, moving down the group, electronegativity decreases. Therefore, boron is the most electronegative in group 13. So now you know that when we are talking about electronegativity, so obviously the next property will come, that is metallic and non-metallic characters. So if we are dealing with the metallic and non-metallic characters, non-metallic characters directly proportional to electronegativity. Greater the electronegativity, more will be the non-metallic characters. Non-metallic characters, bad conductor of electricity, not malleable and ductile, no particular luster, etc. Form especially covalent compound and so on. So if we consider in the group 13, boron is a non-metal. Aluminium is a metal. So aluminium and the other actually, aluminium, gallium, indium and thallium are considered as metal. Gallium sometimes showing some non-metallic characters also, because it is a liquid at room temperature. Okay, its melting point is very low. So that we'll see later on why. So boron, non-metal, aluminium, gallium, indium and thallium are metals. Metallic characters goes on increasing as we move down the group. So we can say that this way, therefore metallic characters increases down the group therefore we can say that metallic characters increases down the group, and obviously non-metallic character goes on decreasing on moving down the group. The next periodic property which we are going to discuss, that is melting point and boiling point. Melting point and boiling point. The melting point actually depends upon the interparticular distance as well as the interparticular forces. In case of boron, there are strong interatomic distance, a strong interatomic attraction. It has a isocohedral structure. It has So boron has a icosahedral structure where each boron is equidistant with 5 other boron atoms, and because of that there is a close packing of boron, and hence boron has the highest melting point. Aluminium has CCP structure, cubic close pack structure or face centered cubic structure. Same for thallium and indium. And therefore, generally we can say this way, as we move down the group, melting point should go on increasing, but here that is not the case. So if we try to plot a graph of melting point versus the elements boron, aluminium, gallium, indium and thallium. So if we try to plot a graph, boron has the highest melting point, then aluminium, gallium, and then further there is again increase in melting point. So why this is so? The melting point of gallium expected that it should be greater than that of the aluminium. So boron must be low, but it is very high because of this structure, and very small intermolecular distance causing the strong attraction between the boron atom, and therefore actually it has a network solid structure. In case of aluminium, there will be CCP structure, cubic close pack structure, same with the indium and thallium. So atomic mass goes on increasing, and therefore there must be increase in melting point, but in case of gallium it is not so. In case of gallium, 2 gallium atoms are close to each other, while 1 gallium atom is associated with 4 atoms. So this is 1, and the 2 atoms are actually far away from these 2 distance. So we can consider that gallium is kind of a diatomic structure. So when I am saying diatomic structure, so these 2 atoms are bonded, these 2, by weak van der Waals forces. And hence gallium has least boiling point. It has a low boiling point that at room temperature it is liquid. It is a metal, but still it is liquid at room temperature. The trend in a boiling point is usual. As we move down the group, boiling point goes on increasing. So there is no exceptional trend in a melting point, boiling point. The next periodic property which we are going to discuss, that is density. Here the mass overcomes the volume, so density goes on increasing as we move down the group. So increasing trend moving down the group. So these are some of the physical periodic properties of boron family. Now we are going to discuss properties which will help to explain the reactivity. So let us consider the general electronic configuration for these elements. Valence shell, that is NH2 NP1. So there is a loss of 1 electron also, or there is a loss of 3 electrons also. So if I consider the property oxidation state, then boron, aluminium, gallium, indium and thallium. If I consider, boron may have a -3 oxidation state because it can accept 3 lone pair of electron. Boron generally form covalent compounds, so it cannot donate +3 electrons, and therefore it is very difficult to form B3 plus. Okay, so if we try to form a compounds like boron halides, the bond is covalent, and if we try to find out the oxidation number, so it may have a +3 oxidation state. Aluminium +3, gallium +3, indium +3 as well as +1, here +3 as well as +1. Now why +1 oxidation state? So one electron is removed from p orbital. Now as we consider moving down the group, then the stability of +1 oxidation state is increasing. +1 is not actually exist for boron, aluminium and gallium. +1 oxidation state is observed for indium and thallium only. It is because of concept called as inert pair effect. Now what do you mean by inert pair effect? So when we are removing one electron, so let us consider thallium, which has a valential electronic configuration as 6s2 6p1. So when the one electron is removed, it gives you Tl plus, and the valential electronic configuration becomes 6s2. Now here we have a paired electrons. For the larger atoms, whenever it has a paired electrons, it becomes very difficult to remove electrons now. So this has now stable configuration, and hence in a thallium +1 oxidation state exists. Therefore, as we move down the group, the stability of +1 oxidation state increases as compared to that of the +3 oxidation state. It is called as it is because of inert pair effect. It is because of inert pair effect. We will see more properties in the next session. Thank you.